Hi again. We are still covering material in Chapter 3 of your textbook, and remember that this chapter includes some of the basic building blocks for inferential statistics. So in the previous lecture, we talked about z-scores and distributions, specifically the normal distribution. Remember that the standard normal distribution is a distribution of standardized scores, also called z-scores, that we can calculate for any individual in our sample. And the standard normal distribution is really useful because we know the qualities of that distribution. We know them really well. In fact, we have some empirical rules that tell us exactly what proportion of scores fall in different areas of the standard normal distribution. We also know that the standard normal distribution always has a mean of exactly 0 and a standard deviation of exactly 1. In fact, we also know that this median and the mode of that distribution will also be 0. And you can think about how we know that based on the information that we've already learned in this class. In today's lecture, I will be talking to you about a few other things that will serve as the building blocks for inferential statistics. And those are the distinction between a sample and a population, and how the sampling process works when we're interested in learning about a particular population. And we'll also talk about probability, and the probability theory, or the way that probability works, is another crucial foundational tool for understanding statistics. Okay, let's move forward. Maybe. Alrighty, so what is the difference between a sample and a population? Let's start with a little example. Imagine that you're cooking, I don't know how many of you like to cook, but imagine you're cooking a pot of beans. And as you're cooking that pot of beans, you're checking it from time to time to know if the beans are done. And if you want to know if the beans are done, the most sensible thing might be to taste all the beans in the entire pot to make sure that they're all done, right? Obviously not. That would be ridiculous. What you do instead, probably, you're thinking, if you're like me, if you're like most of us, you take a spoonful of beans out of the pot and you taste just that spoonful. And if those beans are done, then you might assume that the entire pot is done. Or maybe you want to stir it up a little bit, make sure that you get a good sampling of beans in the pot. And some from the top of the pot, some from the middle, maybe some from down the bottom of the pot close to the burner. After you stirred it all up, you make sure you're getting a good, equal representation from all parts of the pot. And if all those beans are done, then we can assume with some degree of certainty, or confidence anyway, that the entire pot of beans is probably about done. So what you're doing intuitively in that process as a chef is behaving like a statistician. You are sampling from the whole population. In this case, the population is the entire pot of beans. That's the group of things you want to learn about. I want to learn if the whole pot of beans is done. So I want to learn something about my population of beans. But instead of sampling every single bean from the population, I can take a shortcut. I can sample a few different beans from the population to draw an inference about the entire population. Or in other words, to infer that the entire pot of beans is finished cooking. So this is exactly what we do as researchers using statistics to understand a population. The purpose of our research is to learn something about the population. So the first thing that we do is we sample from that population of interest. And notice that we want to make sure that when we're sampling, that we choose a sample that will most reasonably generalize to the population of interest. So this is the part that relates to stirring the pot of beans before you take a spoonful to test. We want to make sure that we get a good generalizable sample, or a sample that is representative of the entire pot of beans, that we're not specifically only sampling from the top layer or reaching our spoon down and only getting a sample of beans from the bottom. We want a sample that's that's representative of the entire pot so we can generalize the information we learn from that sampling to the whole pot of beans. We could think about some other non-food examples, like maybe I want to know how many minutes of exercise the average individual gets in a day. So let's just think about this for a second. Who do I want to learn something about? Who's the population of interest in this example? The population of interest, or the people that I want to learn about, are people in general. I want to know how many minutes of exercise the average person in general gets in a day. So the population of interest here is just people in general, nothing more specific. But let's compare that to the second example I have on the screen. This example says I want to know what proportion of Sac State students are vegetarians. So who am I interested in learning about? I'm only interested in learning about Sacramento State students. So that is my population of interest. So to answer this question, I would sample from students at Sac State. Let's think about how this process works. So we have a scenario that we have a research question, it could be anything, that we want to know about a particular population P. So we'll call the population P. The first question we might ask ourselves is, do we have reasonable access to the entire population P? So if you can just ask everybody in the sample if they're vegetarians, we might as well just ask them if it's reasonable, it's not too expensive, not too time consuming, it's a small enough population that we can access all of them, we might as well just access all of them, right? And then we don't even have to use statistics. We actually have our answer right there in front of us for the research question. We can directly learn about the population we're interested in. Usually this is not the case. Usually we don't reasonably have access to the entire population that we're interested in. This could be all of people diagnosed with autism, or it might be everybody who's between the ages of 10 and 20 in the United States, or it might be all college students in the state of California, right? So whatever the population is that we're interested in learning about, we usually don't have access to the entire population. So this is where our sampling process begins. So we will have to choose a random sample from the population to get a truly representative group of people for the population. So in that case, if you can truly randomly sample, making sure every individual in the population has an equal chance of being selected for your study, that's true random sampling. And I'll say that again because it's important. Random sampling implies that every single person in the population has an equal chance of getting selected for your study or for your sample. If you can ensure that that is the case, then that is beautiful. You can go ahead and randomly select your participants for your study, and you'll generalize to your population based on what you learn from that group of people. If you can't truly randomly sample, then we just do our best with the information we have available. So, for example, if I'm interested in learning about college students in general, I don't have access to all college students in the world, right? So then I ask myself, well, can I truly randomly sample? I probably, in reality, can't ensure that every college student in the entire world has an equal chance of getting selected for my study. In practice, usually I'm going to be over here in this bubble. I'm going to do my best to get a representative sample with the individuals I have available to me. So in other words, maybe I'll just get some college students to answer my survey from Sac State. And there's a little note of caution here that when we're just doing the best with the information we have available to us, we just need to make sure that we don't overgeneralize to the entire population. So I might learn something from the students that I have access to, but I can't necessarily say that they represent all college students in the world. I would have to say There are some limitations to my study. I only had access to college students at a few universities in Northern California. We know that individuals in Northern California may be importantly distinct, culturally distinct, and distinct in other ways from college students in the rest of the world. So these results might not replicate to other college students. Okay, so when we sample from a population, we have a small group of individuals, or it could be a large group of individuals, but a group of individuals that is downsized from the entire population. And with that group of individuals in our sample, we can calculate some measures of central tendency or measures of variability. For example, and most often, we would calculate a mean, a standard deviation, and a variance. And those values that we compute for our sample are called our sample statistics. Well, when we're referring to a population, we could also talk about or refer to the population's mean, standard deviation, and variance. Oh, excuse me, let me get that out of here. So we could also talk about that population having measures of central tendency and measures of variability. In the case of the population, notice that I've introduced new symbols. So no longer do we use capital M, capital SD, and capital SD squared. When we're talking about the population, we use Greek symbols to indicate that we're talking about the population now and no longer talking about the sample. So anytime you see these Greek letters, you know that we're talking about the population level. And we use the Greek symbol mu, that's mu, mu, for the population mean. This here is little sigma for the population standard deviation, and we use sigma squared for the population variance. And those are called the population parameters. So here's just a summary table for you. We have our sample statistics that represent the individuals that I actually have access to, right? So I sample from my population, and of my sample data, I collect my data from them, and I can calculate the mean, the standard deviation, and the variance from those numbers. What I probably don't always know are the true population values, and those are mu, sigma, and sigma squared. If you at this point want to take a break and pause the video, it might be a good time before we dig into some different material, which is probability. So we are going to use probability throughout this course to understand information about the population that we learned from our sample. Let's make that connection a little bit more clear. The purpose of psychological research, or research in general, is usually we're seeking some sort of truth, and that's truth with a capital T, importantly, because we really want to understand the truth about the world. We want to know what's really going on. And we never have access to that actual information, right? So if I have a hypothesis that college students compared to professional workers are not morning people, or in other words, that college students are less of morning people than professional workers, okay? Or would report themselves as being less like morning people. Will I ever know that for certain? Maybe if I have access to all of the college students in the world at every given moment in time, right? And all of professional workers in the world at every given moment in time, indefinitely, then I might know the truth with a capital T. And that could even be argued. But usually we're just working with samples. Okay, we're sampling from the populations to draw inferences to the population. So what I end up doing is I can only make the case that with the information I have in front of me, or with the information in my sample, I can make a case that one thing is more likely than the other, right? Or make the case that it is likely to be true that college students are less like morning people compared to professional workers. I will never really be able to prove something with certainty, without a doubt, to be true about a population. So this is going to be really important in the coming lectures this summer session, because this is really the foundation of inferential statistics. So let's think about this example a little bit more. If we know that one person has a score of 4, okay, so I just close my eyes when I'm out on the street and I point to a person, I say, hey, how much of a morning person are you? And they say on a scale of I don't know, maybe it's 1 to 15, right? And they say, oh, a 4. I want to guess, okay, do I think this person is more like a college student, or do I think that they belong to the professional worker population? Well, if we know that the population of college students has a mean score on the morningness scale of 10, and a standard deviation of 3. Okay, so in other words, I know that this distribution, once standardized, looks something like this, right? A mean of 10, one standard deviation above the mean would be an individual score of someone with a 13. One standard deviation below the mean would be someone with a score of 7. So if someone says that they have a score of 4, are they likely to be a college student? You could think about those empirical rules that you learned about in the previous lecture. A person with a score of 4 is only about 2% likely to fall on this distribution, because only 2% of college student scores fall out in that tail, or are less than 2 standard deviations below the mean of the distribution. So is this person likely to be a college student? Probably not. Well, what about a person with a score of 9? A person with a score of 9 here, that's very close to the average score for a college student. Can I say with certainty that that person is a college student just based on their score of 9 on this scale? No. But could I say that they're likely to be a morning person? Sure. Certainly more likely to be a morning person than the person who said that their score was 4. And this is all the reasoning that we will use in hypothesis testing. So let's just cover some vocabulary that will come up as we use probability. The definition of probability itself is the expected relative frequency of a particular outcome. So breaking that down a little bit further, frequency can be defined as the number of times a particular outcome occurs. And you know that from when we talked about frequency tables. So in a coin toss, if we toss a coin 5 times and it lands on heads 3 out of 5, then the frequency of heads is 3, okay? So the number of times that an outcome equal to heads occurred was 3. Now some more vocabulary. Relative frequency that you see come up in the definition of probability is the number of times the event occurs relative to the number of times it could have possibly occurred. So in the same example, if we toss a coin 5 times and it lands on heads 3 times, then the event occurred 3 times, the frequency was 3, but it could have potentially occurred 5 times, right? We could have gotten 5 heads in a row. So the relative frequency is 3 out of 5. So now the definition of probability has even another word out here. So we're just attaching more words. So expected relative frequency of the particular outcome, that's probability. The expected relative frequency is what you would expect if you repeated the experiment many times. So if I tossed the coin 500 times, how many times would I expect a heads to occur? Or if I toss the coin 10 times each day for 100 days in a row, then on average, I would expect that each session would result in 5 heads and 5 tails, right? So therefore, I can say that if I tossed a coin 10 times, I would expect 5 heads, right? It's your best guess. And we can calculate the probability using this equation. So that's the number of possible successful outcomes over the number of all possible outcomes. So we can calculate it this way. For a given coin toss, the result can be either heads or tails, right? We know that. So the number of possible successful outcomes for heads, right? How many ways can the coin land on heads? Only one way, right? So the successful outcome being a heads, there's only one way that can occur. And how many possible outcomes in total are there? There's 2. The coin could land on heads or it could land on tails. So the probability reduces to 0.5. 1 divided by 2, or 1/2, is 0.5. Let's think of a different example. If we are thinking cards, on any given draw, I want to know what is the probability that I will draw an ace. So how many possible successful outcomes are there? Or in other words, how many possibilities of drawing an ace are there? In a full deck of cards, I know that there are 4 aces, right? So the number of possible successful outcomes, or the number of possibilities of drawing an ace, is 4. And again, if we have a full deck of cards, there's 52 total cards in the deck. So each time I draw a card, I could draw one of 52 different cards. That reduces to a probability of drawing an ace equal to 0.08. And this is actually how people who are card counters, this is how they work. So let's think about probability as it relates to distributions. If I have 50 people and I have a scale score for each of those people on a scale of 0 to 10, so every individual has a score between 0 and 10, what are the chances, if this is my distribution of scores, so this is my histogram, what are the chances of randomly selecting a person from my sample with a score of 9 or 10? Well, I can see, okay, well, the number of possible successful outcomes, or in other words, how many possibilities are there for me to find a person with a 9 or a 10? Well, I see that there's one person here, and one person here with a score of 9 or 10. Okay, so that's my numerator, the number of possible successful outcomes. And then how many people total are there? When I pick someone at random, how many total possible outcomes could there be? Well, I know that my whole sample size is 50, or in other words, that there's 50 people represented in this histogram. So the chances of getting someone with a score of 9 or 10 is 3 over 50, which reduces to 0.06. And that is the end of my lecture on probability and sampling from a population.